Ketos, today we're going to talk about functional groups. Functional groups are super important in organic chemistry. I'm not really a big fan of writing up definitions for us in these videos, but I think that you need to know what a functional group is before we really get rolling into showing you what they are and examples of them. So a functional group is essentially just a group of atoms or bonds that they have a specific, predictable chemical behavior. And what that means is that they're going to behave in similar patterns. So for instance, we're going to talk about a group of chemicals called alcohols, and alcohols have a predictable chemical behavior. They tend to react in very similar ways. Doesn't mean they all react in the exact same way, but that group of atoms or bonds that's similar within that group will essentially force them or allow them to react in a very similar way, which obviously reactions are what chemistry is mostly about. So that's really important. So we're going to jump right in. So before we jump into all of the other functional groups, let's talk about what they're based off of. So alkanes is the name that we give to organic compounds that have only carbons and hydrogens and only have single bonds of those things. And so essentially everything that we do in organic chemistry, whether we're naming, drawing structures, whatever, we're first basing it from the alkanes and then moving from there. So when we talk about alkenes and alkyl halides and all of those things, those are essentially almost everything there is going to be a modification of an alkane structure. So when we talk about functional groups, this is the basics. Everything added to that is a functional group. You don't have to mention alkanes as a separate functional group if you're asked to say identify what the functional groups are, but you should know that that's what a basic hydrocarbon is, meaning that there's only hydrogens and carbons in it and everything in it is single bonds. Okay, so first two functional groups, pretty easy. Alkyl halides. So when you see alkyl, the term alkyl, that means it has an alkane part, in other words, a hydrocarbon part hanging off of it. Alkyl halides means essentially what it sounds like, that it's an alkane with a halogen at some part. And of course, it could be multiple halogens, but any one halogen is enough to make it an alkyl halide. Another thing about functional groups is whenever you see R just means the rest of the molecule, the rest of the chain. In general, it often means an alkane. Okay, so when we have the generic form, this is the generic form of an alkyl halide. That means that there's some chain, and it could be one carbon as far as the chain, okay, but it could be 20. And then the X here means halogen. So it could be chlorine, fluorine, bromine, iodine, any of those. So what I'm going to do, the format I'm going to do for each of these is I'm going to give you the generic form, and then I'm going to give you an example. That example might not correlate directly to the generic form because it could be a little different, okay? So this is our generic form. This would be 1 carbon, 2 carbon, 3 carbon connected to a chlorine. That makes that an alkyl halide. So alkenes, alkene means that there is a double bonded carbon somewhere in the molecule. Again, you'll see several R groups hanging off of here. Those R's actually also, they don't have to be carbons. If you already have carbons in the molecule, they could just be hydrogens. So this could very easily just be 2 carbons double bonded together and hydrogens at each of those points. They could be ethylene or ethene, as we would call it. So double bond means alkene. You'll notice that changes the letter from alkane to an E. That's also going to occur when we do the naming part of this as well. You'll see here's an example over here. 1, 2, 3, 4 carbons. There's a double bond on the end there, so that would be a 1-butene, okay? So that's an example of an alkene. Okay, so next functional groups, alkynes and alcohols. Alkynes, you'll notice again, we're just changing that letter. We had alkanes, alkenes, which meant double bond, and then alkynes, which is sort of the next step, which means triple bond. Okay, so 2 carbon atoms triple bonded somewhere gives us the alkyne. Again, you'll sort of, as we go through this and we get the nomenclature later, which is naming, you'll see that these endings to the functional groups often have something to do with the name as well. Okay, so alkynes, so 1, 2, 3, 4 carbons. Remember that the difference in line structures is when you're drawing a triple bond, you don't just draw it in the line, that it's going to make it linear, and so you got to sort of separate that out a little bit. Our next functional group, really common, alcohols. So an alcohol, we tend to think like alcohol means like, hey, that's the stuff you drink, right? That is a specific kind of alcohol. That's ethyl alcohol or ethanol. Where if you drink any other kind of alcohol, it's essentially poisonous to you. Alcohols are a group of compounds, which mean that you have an OH group somewhere, a hydroxyl group somewhere on the molecule, branching off of a carbon. So we got 1, 2, 3, 4 carbons, and then the OH, which makes it an alcohol. All right, so ketones and aldehydes are our next two. Ketones and aldehydes are related. They look, in fact, if you're looking at them, you're like, it looks like the same thing there. Well, it's a little bit different. So this double bonded oxygen, an oxygen double bonded to a carbon, has a specific name. That is a carbonyl group, okay? And that carbonyl group is what makes something a ketone or an aldehyde. What the difference between the two, between a ketone and between an aldehyde, is where is that carbonyl group. So in the case of a ketone, that carbonyl group is in the middle of the chain somewhere. Okay? That means that you've got a chain of carbons and that the carbonyl, the double bonded oxygen, is not at the end of it. Okay? In an aldehyde, you've got that same carbonyl group, double bonded oxygen, okay, but it's terminal, we would say, meaning that it's at the end of a chain. So in this case, I've drawn two chains. Each of the chains has 4 carbons. The aldehyde, the carbonyl group has to be on the aldehyde, the carbonyl group has to be at the end carbon. On a ketone, it can be anywhere but the end carbon for it to be a ketone. Okay? Obviously, the fact that they're both carbonyl groups means that there's probably some sort of similarity in the way that they work. We'll see that there are going to be some definite differences between them because the fact that you're in the middle of the chain is going to affect some of the electron stuff in a different way than it would for the aldehydes. Okay, so ethers and thiols. Ethers, so what makes an ether an ether is that you have an oxygen. Again, much like we've seen a bunch of stuff, you'll notice that oxygen is sort of a common theme in a lot of these. That we have an oxygen, but the oxygen is essentially taking the place of the carbon in a chain. In other words, it's not like hanging off to the side like the carbonyl group was. It's not just bonded to a carbon and hanging out on its own. It essentially is in the middle of the chain. It's breaking up 2 chains, you could say. Okay, so that means that we've got 1, 2 carbons, 1, 2 carbons. There's an oxygen in the middle. We would typically call that diethyl ether. There's 2 carbon chains of 2 carbons each hanging with the oxygen in the middle there. Ethers probably sound familiar to you because for a long time they were commonly used as anesthetics, and they actually still are in some animal uses and stuff like that. Thiols, you'll notice, look almost exactly like alcohols, and in fact, they're very similar to alcohols, and in some ways they behave like alcohols. Remember that oxygen and sulfur are in the same group in the periodic table, the same column, and so that means they both have 6 valence electrons, and so they're going to behave very similarly chemically in many cases, and so that means that instead of alcohols with an oxygen here, we could have thiols where we have a sulfur taking the place of it. So, sulfides, carboxylic acids, you'll see here that sulfides are analogous to ethers. The sulfur, again, is similar to oxygen in its chemical makeup and its valence electrons, and so we can have a sulfide that is very similar to an ether in some ways. A carboxylic acid, you'll notice that, again, you sort of see what you think is the carbonyl group from the ketones and the aldehydes showing up. What's different about a carboxylic acid is it's got a hydroxyl group and the carbonyl group. Together, these two things are called a carboxyl group, hence carboxylic acid. This is the functional group that makes things organic acids. Organic acids tend to be relatively weak acids, but they're still acidic, and that obviously is going to affect a whole lot of things. Note that with the carboxylic acid, what is necessary here is that, again, it needs to be at the end of a chain to make it a carboxylic acid. We'll see what happens if we get the same sort of group in the middle of a chain here in a minute. So it has to be, again, sort of like an aldehyde, it has to be at a terminal group of a chain. So again, 1, 2, 3, this would be my 4th carbon, carbonyl group, hydroxyl group hanging off together, carboxyl group, that makes that a carboxylic acid.